Good afternoon. This is a video covering a review for my breakout session on electromagnetic induction. If you were absent, or if you just want a quick review over right-hand rule and electromagnetic induction, that's what this video is about. Let's begin. This is going to be a much shorter video. I'm aiming for 10 minutes. So, when we were talking about electricity and static electric charges, let's say I had a positively charged particle sitting in space. It emitted an electric field pointing straight out in all directions. If I had a different particle in some other point, the force on this charged particle was parallel to the electric field lines. Opposite charges attracted, like charges repelled. Everything was pretty simple. Everything was fairly straightforward when we were talking about electricity. For magnetism, that's not quite the case. It's not that simple. Everything happens in 3 dimensions. Let's say I have a current carrying wire. So this wire has some current going through it. Let's say it's going straight up in this case. This wire is going to interact with a magnet. If I took a physical south-north magnet and moved this magnet close to my wire is going to feel a force due to this magnet. Now this force is not going to be as simple as the wire gets attracted to the magnet or gets pushed away from the magnet. Unfortunately, that's not the case. This wire doesn't feel a force up or down away from the magnet. This feels a force from your point of view into the screen or out of the screen. Everything here is perpendicular. All these 3 things, current, magnetic field, and magnetic force, are perpendicular to each other. This perpendicularity is represented and is simplified by using the right-hand rule for magnetic force. If you need to pause the video to take notes, just pause the video and take those notes. I'm not going to wait for that though. So, to find the force on a current carrying wire in a magnetic field, you want to take your right hand, put your thumb perpendicular to your fingers, keep your palm flat, keep your thumb pointing straight out. Take your thumb and point it in the direction of the current. Take your fingers and point them in the direction of the magnetic field. Your fingers are those magnetic field lines. Magnetic field, for this picture down here, points from north to south. So right now, your thumb should be pointing straight up parallel to the screen. Your fingers should be pointing to the right. That leaves your palm pointing directly towards the screen. The force on this wire is going to be directly into the screen. This wire gets pushed. Really, I should say, this wire gets pushed at this center point here. This wire gets pushed into the screen by that palm of your electromagnetic force. Let's look at a practice situation here. I need to draw some field here. I want to draw, let's say my magnetic field is going to the right. I don't want a current going up or down. I'm going to draw a current that, let's say the current is right next to this magnetic field and the current is going into the board. Now keep in mind, I'm just talking about if I took a wire and I pushed a magnet very close to it. So somewhere out in space, I have a very large magnet that I take and I put my magnet right here, and that's creating this magnetic field. So this magnetic field is coming out of this magnet, and I put my wire here. The wire is going to get deflected. In what direction? Well, take your thumb, point it into the screen. Your fingers should point parallel to the field. Your fingers should be pointing to the right. The direction of force, magnetic force on this current carrying wire is straight down. That's one way to look at the right-hand rule. The second way to use the right-hand rule is the inverse situation, when an electric current creates a magnetic field. Magnetic fields are all produced in loops, in concentric circles, around my current carrying wire. So in this case, I'm going to take a single wire that's going to run some current through that wire, and the magnetic field will be curling clockwise or counterclockwise around those loops. Let's say I've got some wire, and it's the same situation. I want my current going into the board. For the curling right-hand rule, you want your fingers curled up like a fist. You want your thumb pointing straight out like a thumbs up. You want your thumb to point in the direction of current. Keep your hand the same shape. Don't uncoil or untwist your fingers or thumb. Keep your hand the same shape. Point your thumb in that direction of current. Look at the direction your fingers are curling. Imagine there's an arrow tip on the very top of your fingers. What direction are they curling? In this case, they're curling in a clockwise direction. And there's not just one magnetic field line going around here. There's an infinite number of magnetic field lines. The field in general points in a clockwise loop around this current I, and it gets weaker the farther away I get. Let's say I have a current coming out of the board. Current coming straight out of the board is this symbol, circle with a dot. Take your thumb, point it in the direction of the current that is away from the screen. Your fingers are now curling, or should be curling, in a counterclockwise direction. And again, there's an infinite number of concentric magnetic field lines going around this current I. Summary of the two ideas so far. A current-carrying wire creates a magnetic field. This is what we just did using the curl rule. That magnetic field curls around that wire. And then let's flip-flop the two situations. A magnetic field creates a force on a current-carrying wire, represented by this equation down here. Force is magnetic field B times current I times length of the wire L. This was our flat hand rule, or flat palm rule. When we combine these two ideas, we come up with Faraday's law of electromagnetic induction, which is that an electric current creates a magnetic field, and a changing magnetic field creates an electric current. Keyword there is changing. You can't have a constant magnetic field because, well, we sit in a constant magnetic field, the Earth's magnetic field, nothing happens. But when you start moving around inside of that magnetic field, or moving the magnetic field itself, you start changing the field and creating some electric current. This is exactly what Faraday invented. This is Faraday's apparatus, also called a transformer. What he did in the top coil, he closed the circuit, ran some current through this top coil. When you get current going through a coil of wire, you end up with a very, very strong magnetic field running through this coil. This very, very strong magnetic field jumps the gap from coil to second coil. In this second coil, it sees there's a magnetic field inside of the second coil. That magnetic field creates a current inside of the second coil, a brand new current, which is registered by this ammeter over here. This is electromagnetic induction. The current is not conducted from one wire to another, it is inducted from one wire to another. That device that Faraday invented is called a transformer, which increases or decreases AC voltages only. AC voltages because we have to have a changing magnetic field. AC voltages are always changing. DC voltages stay the same. A transformer looks like this. This is the important part right here. We have some incoming voltage into my transformer. This incoming voltage goes around a certain number of coils. So I create a very strong magnetic field. That magnetic field flows through this magnetic but non-electrical material. That magnetic field flows through here, inducts a second magnetic field in this second coil with a different number of turns. Now this difference in number of turns creates a different magnetic field, which creates a different voltage. There's an easy ratio between these two voltages and these two number of turns, and that's the voltage out divided by voltage in is equal to the same ratio of number of turns out divided by number of turns in.